Okay, just have to detect.
His first paper is calculating preconditions for parallel workflow. Okay, could you start?
Yes. Okay, hello everyone. Thanks for staying with me for 2 talks in advance. So basically, the 2 papers are extracted from 2 chapters of my dissertation. I'm hoping to actually give you a broader context about how these 2 papers are actually related into a bigger thing. I'll show you some diagram. So first of all, the application domain of these 2 papers are about information systems, where we collect, manage, and provide data. And the emphasis is really upon data rather than algorithms, because you can do simple data transformations to change the state of your system, but subject to business rules and invariants. You have to make sure for every update that you perform to your system, they have to maintain the integrity of your system. And yes, exactly what I said. So I apologize for the small fonts for this diagram. So this is pretty much like a roadmap of my dissertation. So I will actually show you exactly how these 2 papers will fit in to the bigger context. I'll read it with you together. So let me see. First of all, you have some initial user-specified model. Typically, you have some classes, object models really. You have classes, associations, you have methods to change your state. You have some initial models here, which consist of, you have to specify transactions, like atomic operations, and you have to specify workflows, which will be the focus on the first paper. You specify the functionalities of your system, and then somehow you can do a model-based testing of models about your behavior models. And this is the focus of the second paper. So once you have done all the testing and you're sure that your model is actually consistent and complete, and then you can actually generate automatically some working implementation. In the case of my thesis, I generate SQL database. I recently also presented a paper in Japan just a week ago in Kyoto. So that's sort of the outline of the bigger context of developing reliable information systems. So there are 2 things I'm going to present today. One is about how you can make sure the workflows you design is correct. I'll explain what correctness really means later. And the second thing is you want to make sure you can have a way, a formal way actually, to test the model, the behavior model of your information system. Okay, so these are sort of the references of from the thesis. So far only conference papers. I'm hoping to publish more later. So in case you're interested in my dissertation, just Google my name and then just say model-driven developments of the information system, and then it's in the University of Oxford Research Archive. You can actually read the whole thesis. It's free of charge. It's open access, right? So let's talk about 2 important concepts in the case of workflows. We have one concept called guarded transactions. They are updates, of course, but they are actually incorporated with both postconditions and preconditions. So postconditions are the intended effects that you want to apply to the current state of your system, and the precondition is somehow in relation to your postcondition. You want to make sure whatever update you perform on your system will not actually violate its existing semantic invariance after you have completed updates. So you have preconditions and postconditions, and typically we implement the precondition as guards, which means if the preconditions is not satisfied at the current state, we block the operation such that you cannot have any chance to violate the system invariance. Another bigger concept is called workflows. So basically, we want to combine the state effects of your operations. We want to patternize the reoccurring patterns of your updates from operation to workflows. Okay, that's exactly what I said. And the challenging part would be usually if you want to put workflows in parallel, you have a concurrency problem. You want to make sure the interleaving execution of your workflows and their transactions will not have something that's undesirable, which means the workflows are not correct. I'll talk about correctness very quickly, very soon. Okay, so the correctness of workflows. First of all, we have some assumptions here. We have centralized controls, sequential components which will accept the distributed client's request for updates to your system. So we don't have like distributed database. That's not our execution environment. So we have a single sequential data component. And as I said, it is not feasible to actually execute one workflow after another because typically workflow can take a long time before it can finish. So we decide to actually interleave the executions of your workflows. And now, I want to define the issue of correctness. For the workflows to be correct, you want to make sure, okay, so the system state may be modified. Okay, basically, if you want your system to be correct, you do not want either of these two scenarios to happen. The first scenario is some of the workflow instances, they fail to complete simply because the next operations in the workflow, they have their preconditions not satisfied by the current state. So they cannot, and they'll be blocked. As I said, their preconditions are implemented as guards. So if they are not satisfied, they are stuck until you change the state. And the first thing is only about the completeness, only about the successful completion. Even more, let's say your workflows do complete, but the resulting states of your system actually do not satisfy some intended goal specified by the user. For example, let's say you have 100 instances of a reservation workflow in your hotel reservation system. Let's say those 100 instances do complete, but the resulting state does not have 100 rooms available after those 100 instances have been done. That might, the magic word 100 might just be the requirements by your customer. So in general, you can specify all this formally as predicates. Okay, that's basically the, so the contribution of this paper is to address the correctness issue. And we can both specify the problem formally, and we can also to compute the solution efficiently. And we can also prove that the solution is actually correct. Okay, just to give you one very simple example, so an online auction system like eBay. So this is the typical class association graphs or diagram that you can see in UML 2. And for example, an auction has one seller, and an auction has a list of bidders, which is a type customer, etc. Okay, so to actually specify the updates operations of our system, we adopt I adopt the guarded substitution language of the B toolkits, for those of you who actually understand B notation. So we support termination, assignments, parallel composition, sequential composition, bounded and unbounded choice, and generalized parallel composition. Those are the reasonable programming constructs you want to support if you want to specify reasonable updates. Okay, so this is just one simple example. So don't worry too much about what that really means. I will actually give you an intuition about what it is supposed to do. So this is an operation in the context of a customer class. So if a customer actually wants to place a bid for the auction that he has joined, then he has to make sure that his current balance of the account is actually smaller than or equal to the amount he wants to bid. That's by reasonable precondition, right? And here we have some parallel assignments just to update the generated bid information. And this is to say, if no one has bidden on the same option higher than the current customer, then of course you have to set the customer to the highest in the bid. Otherwise, just skip. Okay, that's about operation. And now we specify workflows which will combine operations. And there was actually one paper I just mentioned. So this is a paper I wrote with my PhD supervisor about 2 years ago. And so you can also have a look at it if you're interested. So now we also support different constructs for a workflow. And we also define the formal semantics in the previous paper. Let's just see one example. So now I actually specify 2 workflows, 2 processes. So one is to buy, and the other one is to sell. Okay? So they kind of follow the same structure, kind of organizing the same structure as the operation. The only difference I want to show you is, you can see here the workflows refer to join, place bid, which is the operation we just saw. So they actually combine the state effects of the operations. So let's not worry too much about what the buy and sell will actually say. They're certainly just within your expectation. Okay, now, in order to actually do some formal analysis, we need to have some semantics of our workflows, because if you combine the operations together, you want to see what's the compositional effects of a workflow, provided that the workflow combines several operations together. So I just want to draw your attention to this. Okay, so we want to reason about the progress properties. We want to make sure the workflows can actually complete successfully, and upon completion we have some user-defined goals satisfied. Okay. So in our previous paper, we actually defined some trace function here, and our main motivation for the current paper is to say that trace function is correct, but it is not constructive. Which means if you want to actually apply the idea in practice, you want to have something that's more efficient, and something that's more constructive. Okay? I wouldn't bother you with too much detail of this. So now, that's exactly what I said. So I want to draw your attention now to this property here. I will tell you exactly what that means. For each system trace and some sigma, so sigma and sigma prime means the pre-state and post-state. So this T function here means the trace of the workflow. So after you have applied the state effects of a particular trace from workflow W, there is always at least one T prime trace that can actually allow you to complete the whole interleaving execution. That's actually what the completion property here is saying. So this property here, as I said, it is not constructive because it simply cannot just translate this directly into a C# or C code. It's not constructive. However, that can be a specification of some computationally efficient algorithm that you want to prove against. Okay? So that's the big roadmap of this paper. Right? Let me just go on. Right, one motivating scenario in the eBay example. So I'll just say, let's say a registered customer may be unable to pay the latest winning bid because they are just fluffy. You know, they thought they actually have enough account balance in their bank, but they actually don't. Let's say myself, I actually win 10 bids from eBay, but it turns out my account balance only allows me to pay, let's say, 8 of them. But those 2 of them that I cannot actually afford, it will actually cause the buying processes of those 2 to actually get stopped because no one is going to pay. And myself, I will actually be punished by the system being withdrawn from the membership or something. So that's basically that's one of the many application scenarios that we can apply my approach. So you have a parallel composition of many workflow instances, and if you want to actually know if there's any possibility that the workflows may just not complete successfully. That's really the big picture. Okay, so that's just one possible trace that can actually bring the system to a state to exactly the best scenario we just described. So to actually see more in detail, you can refer to my paper. I encourage you to do that. Okay, now, may not have too much time, but I will just guide you through very quickly about strategy for precondition calculation. I wouldn't go to technical details. They are all in the papers. And for the proofs, they are in my dissertation. You are also encouraged to refer to them if you are interested. Right, so basically, we have to define a way to extract, to do some static calculation of the workflow. So we have to define some traces here. Not to worry too much about it. It's a very simple one. So let's do this one here. So a naive, insufficient strategy would be, if you want to know what's the correct behavior of a set of workflows, the brute force way is to consider all the possible traces in those parallel composition, and then just kind of compute for each one of them what's the completion guard to actually to satisfy. But it's very inefficient because due to combinatorial explosion, if you have parallel composition, we all know that. So this one is correct, but it is efficient. But that's a valid first attempt. Okay, let's not worry too much about it. And just want to draw your attention to this one. So we all know the standard notion of weakest precondition, Dijkstra's weakest precondition. We actually use that intensively to calculate the completion guard. So if you have a parallel composition of two things, you really want to consider what's the order, because you have two things put in parallel, you have two possible orders to consider. So that's actually a non-trivial problem. So our intention is to specify something here, commute, as opposed to complete over here. Okay, we want to replace that by something that's more efficient. Okay, let me just go directly to the computation. So all the details are in the paper. So I just want to show you. Okay, so this is the algorithm that I came up with. It's actually, okay, we have two for loops and one nested loop. They seem quite okay, but it turns out it's very hard to actually prove that they actually calculate the correct guard. So that's really the contribution of this paper. So without going into the detail, I'll show you what's the visual view of that algorithm is trying to do. So basically, we are applying the technique of dynamic programming, which means we are trying to fill in a matrix, two-dimensional matrix actually, and then eventually we'll start from the right. We will start from this cell in the yellow, and eventually we will actually fill in the matrix such that this cell over here is the answer for the completion guard. So that's the intuition, and we do so by, first of all, we fill in these two. The bottom row and the rightmost column, these two, and then we gradually go from left to right, right to left, and bottom to top. So you're guaranteed always, let's say if I want to calculate this cell here, it's guaranteed I have already calculated the result of this cell and this cell, because this guy is in its bottom and this guy is to its right. So we guarantee we have got the result already. And the complexity of this correspond to the number of cells in the matrix, which is much, much cheaper than considering the combinatorial possibility of your parallel composition. Okay, so I will end my talk very soon. I just want to tell you, to actually prove that, you actually have to prove two important lemmas. You want to prove that they're all in the papers. So these two rows actually calculate the correct results as the base case, and then this portion here actually correctly and inductively correctly reuse the result that have been calculated. Okay, so we specify some theorem to say because we substitute commute for complete, and we want to make sure I actually prove that they are actually equivalent semantically. And this is the final theorem I proved. So very quickly, so you have some workflows currently active, and you have a request for a new workflow. You don't know if you should really execute it or not. So what we do is to apply the algorithm I just introduced, and to make sure we calculate something called G. If G actually satisfies in the current state, then we say, okay, the new workflow, you can just go ahead and execute. Otherwise, we block you. Okay, so this, and after we have done all the proofs and all the algorithm specification, and it turns out the problem I just showed you on the online auction system is trivial to actually calculate. Okay, so conclusion. I got a workflow language and some formal semantics from a previous publication. And in this talk, I actually made a non-trivial contribution by suggesting how you can actually calculate the completion guard for precondition as precondition efficiently. And I also prove that it's actually correct. Yes.
Okay, thank you very much. Question? Yes, please.
Is your technique applicable to general programming?
To general parallel programming? I wouldn't say it is. I would say in the particular context of information system, it is. It's applicable. But let's say if you apply that to automotive or aerospace domain, I wouldn't say it is. So I would say still it is actually applicable to our small to medium scale system, where you actually have workflows, and each operations are actually simple data transformations. In that case, it's applicable. Yeah. That's certainly the limitation of the approach. Yes.
Well, as far as understood, you're using dynamic programming to calculate those preconditions. And as this doesn't seem to work in general case, what's the single most important property of your workflows or your language which enables you to use dynamic programming?
Yeah. So there are several important assumptions I make, which of course is at the same time the limitation of the work. First, we don't have distributed database like distributed systems, just one single system. That's why you can actually consider all the workflow that requests or change. And the second thing is our calculation is actually efficient in the case where you actually simply just want to combine several workflows together, where individual workflows do not have very much nested parallel composition. Okay, so you mean if I can just make it more sensible? Okay, let's say.
So could you your answer very concise?
Huh?
Could you answer to the
very concise? Yeah. Okay.
I don't have enough time.
Of course. Sorry. Yeah. I'll make my next talk shorter. It's again me actually, so there's no problem. Okay. So basically, so you can see that. So this part of here is actually corresponds to a sequential workflow, and this part here corresponds to another one. So if the subsystem with sub-workflow that you want to put in parallel together is actually sequential mainly, then they really take advantage of the case of dynamic programming. But if they actually got some nested parallel composition inside, again, you have to calculate what's the possible traces for those parallel compositions before you can apply these matrix calculations.
So that's some sort of independence assumption among the workflows?
That's, what do you mean independent?
In a sense, you consider them separately. They don't interfere with each other.
Yeah, exactly. You want to make sure your workflows, they don't interfere with each other, but you don't want to enforce too strongly.
Okay, thank you very much.
Thank you.
Now we will move to the next paper.